In this screencast, we'll consider a scenario in the blending process where we have multiple inputs and multiple outputs, and we will use the relative gain array to help us design a multivariable control strategy. So in particular, we'll consider the case of two process inputs. We'll consider W1 and W2, and we will have two outputs that we wish to control. Naively, we might set those to be V prime and X prime. Go ahead and use deviation variables for all of our quantities here. However, because volume is an integrating process, we saw in previous screencasts that it does not have a steady state value, and therefore it is difficult to use the relative gain array analysis. So instead, we will use the rate of change of the volume, which does have a steady state, where R prime is dV prime dt. So capital R prime of S is S V prime of S. Now that we have two inputs and two outputs, we can express four distinct transfer functions. So we can have G11 of S, which is R prime of S over W1 prime of S, and that is just 10 to the minus 3. Our transfer function of V prime over W1 prime was an integrating process. It was 10 to the minus 3 over S, but now when we use the rate expression, we multiply that by S and cancel out the S's. G12 of S is R prime of S over W2 prime of S. And similarly, this is also 10 to the minus 3. But then when we go on to our second control variable, X, we have two more transfer functions. X prime of S over W1 prime of S is negative 2.5 times 10 to the minus 6 over S plus 4 times 10 to the minus 4. And finally, we have G22 of S. In this multivariable context, we can also express the overall steady state gain of our system. And we can calculate this as GP of 0. Really, we're just going to write out the gains associated with each term. So we can also think about calculating this steady state gain using the final value theorem, which we saw in an earlier screencast. In that case, we had S, G of 0, and then if we evaluate that for a step input, we get a 1 over S term. And so those S terms cancel, and then we're just left with G of 0 from the final value theorem. In any case, the steady state gain matrix here tells us how an input of unit height will lead to a change in the output. So it's that proportionality constant, or our system gain. And by inspecting this gain matrix, we can actually figure out how we should pair up our two inputs and our two outputs. So we can see from the first row that our two inputs, W1 and W2, equally affect the volume change in the tank. So those gains are equal. So it's not really clear which input we should pair with R. However, we can see that we do have a higher gain for row 2 in X if we pair it with input 2, with W2, because that has a higher gain. So it's actually pretty clear here that we should pair up output 2 with input 2 in a single feedback loop, and then we can have another second feedback loop in which we pair input 1 and output 1. But sometimes it's not so obvious to see that from the steady state gain matrix, and so we can use the relative gain array, where lambda ij is just equal to kij, so we pick off the corresponding element of k, multiplied by hij, where we define h as k inverse quantity transpose. So if we go ahead and calculate h and then lambda, we will get the relative gain array. which in this particular case is 0.75, 0.25, 0.25, 0.75. So ideally, we would like to have all 1s on the diagonal and 0s on the off diagonal. This would indicate that we would have no interaction between our two control loops when we pair up U1 with Y1 and U2 with Y2. So here we can see from the 0.25 on the off diagonal that we do have interactions between our two control loops. And we can see this if we look back at the K matrix. If we want to understand the origin of those interaction terms, we can look back at our steady state gain matrix K. And we can see that both inputs affect both outputs substantially. So if we make a change to U1 to affect Y1, it will also affect Y2 and vice versa. So we will have to understand these interactions when we put together two feedback control loops in this multivariable system.